Hi, in this video, I'm gonna explain about drift and diffusion current. Introduction. Drift current. The movement of carrier due to electric field E, direction of the drift current is always in the direction of the electric field. Diffusion current. The flow of the carrier due to density gradients dN/dx. The drift current always flows in the electric field's direction. Drift current is a movement of charged carrier like electrons or hole due to an applied electric field in a metal material. In semiconductor, the electric field pushes this carrier producing a current. Although drift current also occurs in metals and electrolytes, it is most commonly discussed in the context of semiconductors. When a semiconductor is subject to a voltage, electrons flow toward the battery's positive VE terminal and holes migrate toward the negative VE terminals. In this case, electrons are negatively charged carriers while the holes are positively charged carriers. As a result, the positive VE terminal of the battery attracts electrons while the negative VE terminal attracts holes. Diffusion current. In a semiconductor, current is created by the diffusion of a charged carrier like electrons and holes. This happens due to uneven concentration of this charge. Drift current, on the other hand, is caused by the charged carrier moving due to an electric field. Diffusion current can flow either in the same direction or the opposite direction as a drift current. Comparison between drift current and diffusion current. You may pause the video to look at the table. Drift and diffusion current in semiconductor. Role in p-n junction. Carrier diffusion occurs due to large differences in carrier concentration at the junction. Hole from the p side diffuse into the n side, while electrons from the n side move into the p side. As holes leave the p side, negatively charged acceptor ions near the junction remain uncompensated. Similarly, as the electron leave the n side, positively charged donor ions near the junction are left uncompensated. This creates a positive space charge region near the n side junction and a negative space charge region near the p side junction. Application for drift current. Diodes. In a diode, an electric field exists in the depletion region of the p-n junction. The drift mechanism helps sweep out the minority carriers across the junction, ensuring the carriers generated thermally or via external process are efficiently removed. Transistor. Drift current contributes significantly in regions of the device where strong electric fields are present, such as the channel of a MOSFET or the collector-based junction of BJT. Helps in carrier transport, ensuring efficient current flow and application. Application for diffusion current. Diodes. Diffusion dominates in the forward bias operation of a diode, where carriers diffuse across the p-n junction due to the concentration gradient created by the bias voltage. The recombination of the carriers in the quasi-neutral regions ensure current flow. Transistors. In the BJTs, diffusion is the primary mechanism for the carrier transport in the base region. Electrons or hole injected into the base diffuse toward the collector. This diffusion mechanism is critical for achieving application in BJTs. This is the visual demonstration about drift current and diffusion current. 1. p-n junction structure. Show p-type, n-type and depletion region. 2. Diffusion current. Arrow showing carriers moving from high to low concentration. 3. Drift current. Arrow showing carrier movement due to the electric field and in the depletion region. 4. Equilibrium. Overlapping drift and diffusion current balancing each other. 5. Forward bias. Carriers diffuse across the junction creating a net current. 6. Reverse bias. Drift current dominates as the depletion region widens. To conclude all that, analyzing the behavior of a semiconductor device, such as p-n junction, depletion zone and carrier transport mechanism, requires an understanding of a drift and diffusion current. This information makes it possible to accurately model and optimize electrical equipment, improving their dependability, speed and efficiency. This idea provides the basic for technical advancement including high-speed communication system, CMOS security and LEDs. They also have a real-world use in the integrated circuit, sensor and photovoltaics, where drift and diffusion current interact to affect device performance greatly. That's the end of our video. Thank you for listening.